All right, so we're going to talk about equilibrium and dissolving. And specifically, we're going to be talking about Ksp, which is the solubility product constant. And so if I have a little lump of solid here, let's call it magnesium fluoride, MgF2, and that is a solid, and it is at equilibrium with its two ions, Mg2 plus aqueous and 2F minus aqueous. The reason we're saying it's at equilibrium is because if you put some solid into a beaker with some water and you stir it around and not all of it dissolves, we are at a situation where the solution is saturated. So we've reached the point where the maximum amount of solid can dissolve. And so then if that's the case, that means we're at equilibrium, because it's not just a static state, it's a dynamic state. So you've got some solid crystals dissolving, even though it just kind of looks like the same amount is sitting there at the bottom of the container. Some of the crystal is dissolving, but at the same rate. So you can see my up arrow, that's dissolving. At the exact same rate, the down arrow represents recrystallization of some ions. So it's reached equilibrium at the point where we say that the solution is saturated. Now we've got our reaction. We could talk about, since it is an equilibrium system, just like any other equilibrium system, we could write an expression, right? So that expression is going to be called a Ksp, or solubility, the SP refers to solubility product constant. So our reactant is a solid, so it gets left out. So all we're really left with are two aqueous solutions. So our magnesium ion and our two fluoride ions. And so if we write the expression for this, the magnesium is just we're going to say concentration of magnesium. But the fluoride has a coefficient of 2, so it's going to get an exponent of 2, and that's our expression. So that should be pretty straightforward. We've done that before with other kinds of reactions. So let's talk about what this means in terms of solubility. Let's say I actually know the value for this. We look it up and we get a Ksp for this reaction. Of course, like any other reaction, it is constant only if the temperature is constant. So at 25 degrees Celsius, the Ksp for this particular dissolving process is 6.4 times 10 to the negative 9. All right, that's our Ksp value. So what if I want to know how soluble, or we can say what is the molar solubility of MgF2 at 25 degrees. All right, and it's not that hard to figure out, because when we talk about molar solubility, we're just saying, like, how many moles per liter can we get dissolved? All right, so if I set up an ice box, start there. So I'm going to just kind of recopy the equation down here for the purposes of our ice box organization. 2 plus, and then 2F minus, and these are both aqueous. Okay, now we have our initial, our change, and our equilibrium. The solid we don't worry about, it doesn't really have a molarity. Our two products, of course, start at 0, just like always, but they're going to go up by an unknown amount. The only thing we do know is that the fluoride will go up by twice what the magnesium goes up by, right, because of the coefficient of 2. So we're going to, instead of saying that it goes up by X, we're going to say that it goes up by S, just because that's sort of the convention for solubility. All right, and then, of course, that means that the F minus is going to go up by 2S, right? And so this becomes 2S at equilibrium, and this becomes just S. And then I can go ahead and set it equal to my Ksp. So Ksp equals, And then if I think about my expression that I wrote earlier, it's just going to be S times, and then so that takes care of that. And then our 2S still has to be squared, right? Because that's what the expression says. So it's S times 2S squared, and we have to figure out what S is. All right, so we've got some like terms, obviously, we can combine. We can also square not only our S, but also the 2 as well. So that's going to become 4S squared, right? So 2 to the second power. And then we also take the S to the second power. And then we still have to multiply by this S over here. So instead of 4S squared, we end up with 4S cubed. And I said that that was equal to KSP, but actually we know what our KSP is, so we can go ahead and plug that number in, right? So that is equal to 6.4 times 10 to the negative 9. And now we just solve for S. Okay, so we're going to go ahead and take the cube root and divide by 4 on both sides, right? So cube root, divide by 4, that takes care of our exponent and also takes care of the 4. So cube root, make that a little bit bigger, divide by 4, and that gives me S equals 0.0012, and that would be molar. So that is the maximum molarity that I can get for magnesium fluoride at 25 degrees Celsius. Now, one thing I want you to notice is our KSP being equal to 4S cubed. We can figure that out with an icebox every time, but notice it would really have to be the same. That 4S cubed is going to be the same anytime I have 1, 2, 3 ions that a dissolving process creates. So it should give me the same format, 4S cubed equals KSP, and then we just solve for S every time. All right. And then if we're creating 2 ions, let's just say hypothetically we've got like, we'll do a simple one, NaCl solid goes to Na plus Cl minus, right? We could do the icebox, but what we're going to end up with is just that these two are exactly the same because they don't have any coefficients, and so it's just going to be KSP equals S squared, right? So anytime you have 2 ions on the product side, you're going to get KSP is equal to S squared, right? Anytime you have 3, it's going to be 4S cubed. Anytime you have, let's say 4, like let's say you have aluminum nitrate. Okay. All right, so we're going to get Al3 plus 3 NO3 minuses. So your KSP would be concentration of Al3 plus times concentration of NO3 minus to the third, right? So we're going to end up with KSP is equal to S times 3S cubed, right? And so that's going to end up being the same thing as saying KSP equals 9. Oh, wow. I just made the mistake I was about to warn you guys not to make. It's not 3 times 3. It's 3 to the third power. So, sorry, 27, right? 27 S to the fourth. So you will get that every time you have 1, 2, 3, 4 ions created. Okay. Again, you don't have to memorize that. You can work that out, but might save you a little bit of time if you kind of have that in mind. Okay, and then the other thing we need to talk about in terms of just introducing Ksp is Ksp insolubility can be predictable, but only if compounds do have an equal number of ions. So we just got done talking about these different Ksp setups that we can get. You know, if we have 2 ions, you know, like we did with sodium chloride, then we end up with this S squared situation. If we have 4, we have 27s to the 4th. If we have 3, we have 4s cubed. So if they are the same number of ions, though, like magnesium fluoride compared to calcium chloride or something like that, something else that has 3 ions, it is actually pretty predictable, okay? So, for example, here's a little question from one of our problem sets. It says 3 saturated solutions, X, Y, and Z, are prepared at 25 degrees Celsius. Based on the information in the table above, which of the following lists the solutions in order of increasing concentration of silver? So that just means which one is most soluble, you know, least to most soluble. And if all of these are, you know, 2 total ions, and they are, right? Silver bromide is 2, so silver chloride and silver iodide, all 2 ions. Then they should all have the Ksp equals S squared, you know, relationship. And so that simply means that the one with the largest value for Ksp would also have the largest value for S. And so it becomes pretty predictable. So since these all have the same number of ions, we say the least soluble one, because we're going in increasing order, would be the one with the smallest Ksp. So that would be Z, right? So Z is smallest. And then second smallest is X. That's our silver bromide. And then the largest would be Y, which is silver chloride. Now, if you were given a similar question, but they didn't all have the same number of ions, you would actually have to do the math, because it's not something you could just look at and figure out, generally speaking. If 2 of them had 2 ions and another one had 3 and they all had different Ksps, it's going to be a little bit trickier and you want to actually do the calculation. So go ahead and stop there, and we'll pick up with predicting precipitate formation next time.